Hand a single, complex corporate job to an autonomous AI agent, and it might succeed. Hand the exact same job to a swarm of 144 agents running simultaneously, and the system collapses. These systems usually run on what is known as a loop architecture. You give a large language model an open-ended goal and a box of tools, and it dynamically guesses what to do next, step by step, until it decides it has finished the job. That exploratory freedom is expensive. With the AI making real-time sequential decisions, execution is slow. You pay for a constant, unpredictable stream of input and output tokens as the model attempts to find its way toward an answer. If you are running standard operating procedures, trial and error is a severe liability. You cannot afford an agent deciding on Tuesday to process an invoice differently than it did on Monday. Total autonomy works for open-ended research. But when a business requires strict compliance and repeatable execution, granting an AI total freedom becomes an operational hazard. To fix this unpredictability, developers are moving away from open-ended agents and building structures known as graph engineering. The difference lies in the framework. On the left, the loop architecture circles back on itself as the agent continuously guesses its next move. On the right, the graph architecture lays out a strict, predetermined map. Notice how the graph branches outward. Because the path is mapped in advance, multiple nodes execute their tasks at the exact same time. To build reliable infrastructure, you must replace sequential guessing with deterministic routing. Map the dependencies, group the standalone tasks, and run them in parallel. Applied AI engineering is shifting away from building smarter autonomous agents and toward architecting highly disciplined deterministic tracks for those models to run on. Let's trace a concrete example. Imagine a workflow designed to gather morning briefings. It needs to review GitHub pull requests, scan a calendar, and search the web for industry news. In a graph setup, this architecture maps to a central starting point that immediately splits into 4 separate simultaneous branches: web search, GitHub, calendar, and memory. Software engineers looking at this will recognize it as a directed acyclic graph. It looks identical to the data pipelines built in Apache Airflow for years. However, there is a mechanical difference. In a legacy DAG, the nodes execute predictable Python or SQL, and the connections between them are hard-coded rules. In an AI graph, the nodes contain non-deterministic large language models. The edges connecting them are routing decisions made by LLM classifiers evaluating the context of the data in real time. You are taking the rigid, predictable plumbing of a traditional data pipeline and pumping generative intelligence through it. To migrate a process from a loop into a graph, you have to identify which steps genuinely rely on each other and which are just illusions of sequence. We often arrange tasks in a straight line out of human habit. Here, 4 steps pass data sequentially. Apply the arrow test. An arrow only belongs if the downstream worker absolutely requires the upstream output. If step 3 doesn't actually read what step 2 writes, the arrow is an error. Forcing nodes to wait when no data crosses wastes compute time for zero operational benefit. Steps failing the arrow test get reconfigured. They shift into a vertical stack, executing in parallel before handing independent results into a single synthesis node. There is a cost trade-off here. You pay for the input context at the start of every parallel node, meaning your overall token usage increases. The return on that investment is a massive reduction in waiting time. Eliminating empty arrows transforms a slow sequential crawl into a high-speed parallel sprint, optimizing the unit economics of the entire workflow. When you start executing dozens of LLM calls in parallel, you immediately hit a hard infrastructure wall. This chart tracks concurrent API requests. If you deploy 144 asynchronous workers to hit an endpoint at the exact same millisecond, the request line violently spikes, the system crashes, and the operation instantly drops to 0. API providers like Anthropic or OpenAI trigger these burst rate limits to protect their infrastructure from sudden massive spikes in request volume. The solution is a mathematical governor called pacing. Instead of launching everything at once, cap in-flight requests based on your hardware. Everything past that limit sits in a queue, waiting for an open slot. Infinite parallel execution is a theoretical illusion. To build a system that scales, your architecture must respect the hard physical limits of the third-party APIs you rely on. Once you have data flowing quickly and consistently through the graph, the next structural vulnerability is the accuracy of the output itself. Relying on standard execution logs is dangerous in this environment. An LLM will frequently return a success code indicating the syntax finished perfectly, even if it entirely hallucinated the actual meaning of the task. To catch semantic errors, you insert verification nodes into the workflow. Think of them as adversarial gates dropping down over the arrows between your steps. The only job of a checker node is to aggressively audit the data. It tries to refute the claims, find logical gaps, and kill the finding before it can travel downstream to the user. If you use multiple checkers, you have to introduce prompt variance. Sending 3 checkers to ask the exact same question will yield the exact same blind spots. They must evaluate the data from different semantic angles. When you build with non-deterministic models, a clean execution log proves nothing. The only metric of success that matters is data surviving an adversarial, semantically diverse audit. So, does moving to a graph framework mean loop engineering is completely obsolete? Not at all. Graph engineering encapsulates the loop, controlling its blast radius. If we zoom deep inside this node designated for deep research, you'll see a microloop spinning safely inside. For tasks requiring dynamic exploration, drop an agentic loop into a walled-off node. This hybrid setup provides the best of both worlds. You maintain the strict speed and cost controls of a deterministic macro architecture while leveraging the exploratory capabilities of a loop exactly where it is needed. The operational mandate is clear: map dependencies to eliminate empty arrows, enforce pacing to survive rate limits, audit outputs by their semantic meaning, not just their completion status. Scaling AI infrastructure requires moving past total agent freedom and instead architecting strict deterministic boundaries around a model's non-deterministic brilliance.